most of the results I will talk about today are not my results. I would like to introduce the results of my collaborators. Moscow State University, because I believe that they are interesting to this audience, and questions which arise are maybe even more interesting. So, however, some of my results will pop up in some places. So, let me begin with a simplistic example. So, let's consider an ODE with, let's say, initial condition. And we would like to understand how this ODE behaves near this point. So the question is to understand the solution around t is equal to 0. So, of course, one can solve this equation and see this exponential function, and then this is almost it. However, let's pretend that we don't know that it's an exponential function. Then, another thing that you can almost always do is to look for a solution as a power series of the form a k t to the k, from k from 0 to infinity. So if you plug this power series into the initial equation, what you will get is a system, an infinite system of algebraic equations in A, because what we will have on the left-hand side, we will have derivative of this power series, so it will be a1 plus 2a2t plus ... It will be equal to a0 plus a1t plus ... So one can equate coefficients near the equal powers of t, and from this you can find as many a's as you wish. So you can find out, so from initial condition, you know that a0 is 1, then you will find out that a1 is 1, and you'll find out that a2 is 1 over 2, and so on, and so you will get what you are supposed to get, the Taylor series of the exponential function. So, and since this is Taylor series, and it actually converges quite fast, you can get very accurate values of the solution without actually solving the equation in strict sense, without solving it in closed form.
And so things like what you're suggesting, are they for equations with constant coefficients? With what kind of things?
I will generalize it. This was an example. So, and this can be done. For ODEs with constant coefficients. ODEs.
Not necessarily linear.
Not necessarily linear, yes. For algebraic ODEs with constant coefficients, and actually, if coefficients involve t, this is still fine.
As long as
they involve a polynomial.
Okay.
So also over rational functions, but in this edition there will be some subtleties. Not at every point you can find such an equation.
Right, and also so that the right-hand side would make sense under the substitution of the initial condition, right? So
yes, right. Otherwise, of course, it doesn't make sense.
Under the sufficient conditions for uniqueness and
yes. So if there exists a solution, then you can.
If there exists a unique solution, then you can do that.
Yeah. Okay. Yeah, maybe this example was a little bit misleading in the sense that I don't require it to be solved for the highest derivative.
You're not.
Any polynomial ODE.
And you don't need the solution to be unique, or do you?
I don't need actually in examples which I want so to speak to avoid. It will be not unique.
Right.
I will show an example, and like this is a good example. I will show a bad example in a moment, and we'll explain what's wrong with it.
Yeah, but do you want unique solutions? You
No,
don't want.
I don't
You don't
require.
require that.
I don't require.
Okay, you can handle that.
Yes, yes.
So do you allow the implicitly defined ODE?
What do you mean by that?
You
Yeah,
mean-
like y squared, y prime squared. That's what he said. Yes.
Yeah, yeah. So for example, let me just write just some example from the top of my head. Plus y minus y squared 0. This is fine for me. Okay. So this is fine for me, although it's not solved for the highest derivative, and it actually could be second order. That's still fine.
Sure.
So just these equations will be a little bit harder, but they're still polynomial equations. It's still something what can handle. So, and this is some general approach to work with any polynomial ODEs. So algebraic ODEs. So you can try to find solution as a power series, and then use some truncation of this power series to get some numerical data.
So this is for one dependent variable.
Yes, but there are no restrictions. I mean, you can do the same if there are two variables.
Okay.
You can plug two power series. That's, the advantage of this approach is very general. No, doesn't.
But now, in
Like-
practice, you may not be able to actually compute those coefficients infinitely. You may only be able to go out to some stage.
Sure. I will.
Yeah.
Of course, I will not be able to compute all of them. However, and that's the point I'm coming to. So
Convergence.
if the series is convergent, then, for example, in this situation, you will get very good results. Okay, so if solution converges slowly, then you have to compute more. But the very bad thing that can happen is that solution actually diverges. So in the first,
Can you detect that?
that's what I will be talking about today almost all the time.
Can you not? Yes.
So other people can detect it for a single solution. Results I will talk about, they will say that such equation does not have divergent solutions at all. So I will present some local results for single solution and some global results for a single equation.
Okay, now the question might look misleading, the one that you stated there. Just to understand this solution around.
Yes. This I didn't say that this is the main question of my
But you
talk.
state the main question.
Yes, so the main question is given.
Could you write it down?
Okay, yeah, okay, you're right. So, now main question. Given algebraic ODE, so maybe the most important is
With
whether
initial conditions.
without initial conditions. Without. First, whether it has divergent solutions.
So determine.
Determine, yeah. So the question is given, yeah, determine.
So you're not talking about systems?
Pardon?
You're not talking about systems?
Given, I will talk about systems.
So the general question is still about
system of algebraic ODEs.
Yeah.
Even system. Determine if it has divergent solutions.
What's the meaning of a divergent solution?
So form a power series that satisfies equation and doesn't converge in any neighborhood. So that this power series is, from the first glance, useless, although it's actually useful. So, and
Doesn't having a power solution require having an initial condition? At least in this first example, it did. Because you needed the initial condition to get a zero.
Maybe
Yes, yes,
This
so-
means if there exists an initial condition,
Yes, it's a, so
it's invalid.
yes, it's quantified.
For
So
example,
in this situation, I have one solution because I specified initial condition. If I don't specify initial conditions, I have a bunch of solutions, infinitely many, and my question is whether at least one of them is divergent for any initial conditions.
So you see, for example, even the question of unicity varies
Right,
upon
sure.
the
Right,
specification of initial conditions.
Right, yeah.
So things could go worse if you change initial
Right,
conditions.
yeah.
And another question, if there are divergent solutions, how to find corresponding initial conditions?
You mean the initial conditions for the divergent
Yes.
solutions?
Yes.
Well, or for the convergent, it's the same thing.
Could you clarify the meaning of determine and find? The precise meaning. Is it you want to keep it vague and
I want to keep it vague, so I will present not one single result, and they will give some conditions for equations. So I will present, for this I'll present the result that if equation satisfies some properties that it doesn't have, divergent, and here I will explain that if it has, there are not so many of them. They are located in some, so to speak, hypersurface.
Okay.
So-
in other words, typical math answer. So not it's not an algorithm, and it's actually.
Oh, no. So, okay. Both of them can be efficiently checked.
Effectively checked.
Effectively
Effectively
checked.
checked.
Is
And I
your-
will talk about it.
Okay.
So is what you found necessary and sufficient?
No. Necessary and sufficient, you see, it's very hard. Because convergence is a very subtle analytical property.
Yes.
So working on algebraic and symbolic level, it's actually surprising that we can say anything about convergence. Something. And we can, and that's really surprising. So to hope that we can actually test convergence using purely symbolic methods is, I don't believe in that.
So what he's saying that a necessary and sufficient condition is hopeless,
It is from my point of view.
and already the conditions he
Conditions
presented
with-
is an achievement.
Yes.
That's what he's saying.
So you're saying that you can find certain initial conditions where you know for sure that it has divergent solutions? That doesn't make any
For
sense.
this, no. I can say that if divergent solutions exist, their initial conditions have to lie in some region.
Why
So
are you-
therefore it's
so why are you
convergent
interested
outside.
Why are you interested
Yeah.
in divergent solutions and not convergent solutions?
Well, he's interested in convergent solutions.
Yeah,
He just wants to see
I-
where
So
the
how do you
bad ones
apply
are.
how do you apply that to convergent solutions?
Because
To
if
see what the bad ones are.
yeah, so I want to see where bad ones are and not go there.
So is it the same thing as finding where the convergent solutions are?
Guarantee that to find a big set of initial conditions for which all solutions are convergent.
Yes. So
Almost everywhere. So, but he will say that for sure in this big set, the convergent solutions are.
So could you specify exactly the corresponding initial condition? What is the property of these initial conditions?
I will specify
That's
the
the purpose of the talk.
result.
No.
This
When
may-
we say find the correspond to what?
He
To divergent
wants
solutions.
to say vague. So he says
Yes. So
it's for
this is like
some
general questions. I don't want to specify it very precisely because this is like a big question, and I will give some answers to it, which will be precise.
Now what if I can tell you, given your system, the initial conditions where I can guarantee you existence and uniqueness of solution locally? What if I can give you that? Does that answer your question or not? Is it the same question or is it a different question?
This is partial answer.
which is better?
What do you mean by better?
I mean, the problem that I supposedly solved and the problem you supposedly solved. I'm looking at it for finding, if I can find you necessary and sufficient conditions for the initial values that guarantees the existence of unique solutions. I didn't say convergent, but I suppose that could mean convergent. Then
Well, if you say
Then the
it
complement
means
will be
it's-
where
it's
divergent.
convergent.
that's right.
So,
So it
same
solves that
thing.
problem. That's
Same
what I
thing.
was thinking. But he said this is not necessary and sufficient.
No, all he's saying is the places where it fails is on some hypersurface.
Sure. I mean,
Yeah.
this is con-
So
yeah,
there's a
sure,
bit,
sure.
so there's a complement of the
So I-
hypersurface, you're in good shape.
Okay, so I hate really to promote my own work, but I mean, 2 decades ago, Pritchard and me had a paper on initial conditions for exactly that system.
That kind, you mean
Algebraic
algebraic ODE?
ODE systems, yes.
Okay, that's good. I will look at that.
Okay, thank you.
I'm not aware of it so
Yeah.
far. Thank you for letting me know.
And there is an algorithm to do it. To
Okay,
actually
good,
compute
good,
that.
good. Okay, so actually, main thing I will talk about is this one.
Okay.
So there are just
So
there are no.
that's why I want to understand, is there a difference between the problem, let's say, in our paper and this problem? Because you're thinking about it on the divergent side.
Okay, I want to make sure that I don't have divergence, so to speak. Okay, let me just continue and I will formulate results, and I think that it will.
Sounds like a good plan.
Okay, all right, let's go on.
Okay, so first of all, I want to show an example which I would like to avoid. So how solution can diverge. It will be actually a system.
William, by the way, so that the presentation flows, maybe you could present next Friday that result, so
That probably has been presented before, but if you like, sure. No, if you like.
Okay, so then this will go faster.
All right, okay. But it's 20 years ago.
So by direct computation, one can check that these two power series satisfy the differential equation, the system of differential equations. It's just computation. And this n factorial, it kills any conversions. So this system,
It's
this
a linear equation. In fact, so it's a scale.
in fact, it's linear. Yes, that's
Linear
so.
equation.
And it's small linear equation, and this phenomenon already occurs. So the phenomenon is actually a serious one. So and this n factorial, it forces the series not to converge in any neighborhood of 0. So such things happen, and they happen even in small examples. And I don't want to leave an impression that this power series is completely useless. It's actually very useful because it says a lot about solutions, but it's more tricky.
And by the way, what's the actual point of writing this as a system? So did you really want to enforce constant coefficients?
Yes,
For some other reason? That
yes, for some presentation purposes, mostly.
Okay.
Okay, so
And by the way, is this some kind of classical example, or
it is classical example, and this is a classical question. I will just right now review some prior results. So can you read that? So I want to review some prior results, and actually there is a lot of research about this convergence question. So since it's all these results are somewhat orthogonal to the results I will talk about today, in the sense they answer a little bit different question, I will not review all of these results because that will take a lot of time. So as far as I understood, it goes back to Maia and more than 100 years ago. So there was like first theorem which addressed this question, and then I will just mention some names, and it will not be an exhaustive list. So then it will be and I will explain what these results were. And so
You're missing.
oh yeah, right. I'm sorry. Thanks. So in this line of research, the question was, you are given a power series solution, its truncation, and you want to know whether this specific power series solution will be convergent or divergent. Okay, so this line of research, it first focuses on a single solution.
I don't understand. So you're given a truncation and then what? You're asking for convergence?
Yeah, so you're given truncation enough to continue it uniquely. You are given enough initial conditions so that the power series will be
given an
totally
equation also.
Yeah, sure. Yeah. You're given an equation and enough initial conditions to specify solution uniquely. And then you're asking whether this solution will be convergent in any neighborhood, this particular. So this is about single solution. And all these results are actually also about single equation. Single equation, but with non-constant coefficients over C of t.
And you got that example from one of their papers?
Yeah, actually, I got the sample from textbook in differential equations.
Okay.
I think it's even older than my paper.
And what would be that thing that you said applied to that solution? So what initial conditions you're supposed to specify for that?
So in this situation, two initial conditions I think is enough. So the value of y is 0 and the value of first derivative of y in 0, I think it will be enough to then you will just continue try uniquely. So and actually the theorem of Maillet already somehow explains this example in some sense. So I will just.
So does it have only one bad solution?
Yes. This is the only best
So
solution.
the bad solution is unique.
Yes, the best solution is unique. So
No, but the point, of course, is this has got a pole at t equals 0.
That's right. Of course, yeah. That's so. And finally, all these results they give some necessarily sufficient conditions. Again, not some necessary and some sufficient conditions in terms of some Newton polygons.
And the equations are linear?
That's what I will talk right now. So in these two, this is linear case. Linear over C of t. And this is generalization to nonlinear. So, and
they still do Newton polygons.
yes, and the reason is that since you are focused on single solution, you can linearize near the solution. And then you are back in linear case.
Okay,
So-
is that what they do? They just went the reduction to the...
So I wouldn't say that just reduction. That's reduction. So that's not real thing. And actually they can do more in a sense that they can also say that if it's divergent, it diverges not worse than something. So they can also bound the rate of divergence. And this will come from slopes of Newton polygons. So the results I would like to present, they will not be focused on a single solution, they will be focused on the equation without specified initial conditions. So I will first formulate
Is their argument proceed sort of like this, like showing that there has to be a pole for that, in order for that solution to be divergent?
yeah, so Okay, for a single equation, this is a good intuition. So divergence often happens. So actually, even better intuition is to say that like separand is 0. Because if separand is non-zero, then it will be always convergent. That I will mention that. So. So theorem, this is Razmyslov and last year.
Could you break the chart? Thank you. Yes, thank you.
Okay. So, we consider a system of algebraic ODEs over C with two properties. So first property is that the system defines prime differential ideal.
Which means that the minimal radical differential ideal is prime. Is that what you're saying?
Actually, yes. I will reformulate this theorem in more algebraic terms later.
Okay.
It's just for keep it on equation side. And another thing is that the quotient by this ideal of the ring of differential polynomials has transcendent degree one. Over C.
Over.
C.
What about C of T? So you're not talking.
No, not over
Not
C.
yet. Not yet.
Not at all. It will not be true if I replace C with C of T. I will actually because of that example. So and then
You
if
stated the result.
yes.
And by the way, so a comment. It's 1. It's not a 7. It's a 1, right?
Yeah, it's one.
It's a 1.
Okay, I can let me just write in words.
Okay, thank you. Now, so you're doing this for those systems that define a prime differential ideals. So it's known that it's overall it's a hard question to check.
Right.
But however, I suppose that you mean to apply it for systems for which it's already known in advance for some other reason that the ideal is prime.
Right.
Okay. And there are
So
many of those.
yes. So yeah, and the conclusion is that then all solutions are convergent.
All solutions converge at any initial value.
At any initial value.
Okay.
So if you have such equations, you just don't need to worry about possible divergent solutions because whatever initial conditions are, you don't have them.
So in terms of the initial domain, let's call it, it's the whole space.
What's initial domain?
Well, it's all those places where things.
rephrasing your example.
Okay, yes, that
I
can
mean,
be.
because in general, the initial domain is an algebraic variety, right?
Right. So,
Because they said they have to satisfy some certain order zero equations, so to speak.
right. What do you mean by order zero equations?
They're constant. They're constants, right? Initial conditions given as constants, so they satisfy algebraic equations just by
Okay.
plugging it in there. In fact,
Could you say again your question, if it is a
So,
question.
so if I put t equals 0 in that equation, right, for all the other things, and so that's a set of initial conditions I give, right? I give you what x at 0 is, I give you what y at 0 is, I give you what y dot at 0 is, I give you what x dot at 0 is. They have to satisfy those pair of equations, because that equation is satisfied by initial conditions. Right?
Yes.
It's not talking about that example. It's
No. I'm just
one.
using that because it's on the board.
Yeah, but you still
I'm saying that if
don't
you-
ask me a question.
No. So if you're given an algebraic system of ODEs,
Right.
and I have a set of initial conditions, right, which are just complex numbers in some sense, right? It's easier to overcome that.
Okay.
You plug it into the system, it has to be satisfied,
Right.
okay, for any solution,
Right.
okay? So therefore, they have to satisfy some algebraic equations. That's all I'm saying. Okay? And so in those terms, you're saying that that initial domain is the whole space.
Right.
Okay.
Right.
Whole space in the sense of jet space, of course.
If you wish.
William, so since you will be present next Friday, how about we postpone that?
No, I'm just trying to understand what he's talking about, that's all.
Ah,
I mean,
okay.
I'm not,
Okay.
You're not asking a question, you're making a comment anyway.
yes.
So what is the differentiation with respect to if you're over C? So you got a variable T floating around in the background.
Like here. So I wrote this example intentionally with this additional equation to fit into the whole scheme.
So what is the simultaneous degree?
And here the standard degree is 2. 2, so this one at least can be improved further without any further restrictions. So now,
But you don't have a converse.
of course not.
Okay, well, I don't know. But not.
Moreover, I will present a strength version of this result.
Okay.
Which will be a strong version, which will be not for standard degree 1, but with additional restrictions.
Okay.
Okay. So now I want to formulate this more algebraically and give two ingredients which actually sum up to this fact, because those ingredients are important on their own. So,
By the way, a proof of this, is it, what kind of thing is it? Is it actually differential algebra, or is it like something ad hoc?
I will give you two ingredients. Both of them will be not differential algebra, but they will have differential algebraic corollaries, which will give that.
Yeah.
So I will give, roughly speaking, a sketched proof. So
Okay.
not the full, but just main ideas which are important, I think, on their own.
Okay.
So I want now to move to more differential algebraic setting. So because since my main number here is this transcendent degree, so I would like to move to this quotient. So if I have a system of algebraic ODEs over C, this is the same as to have A, which is differential algebra over C. Because I can generate ideal here, take quotient, and get an algebra.
So it's through differential, not radical.
Yes, but I can take because so yes. For this talk, taking radical is always harmless because radical that doesn't affect solutions in power series.
Okay, so it doesn't matter.
Yeah. So you can also take radical.
So it's not one-to-one thing. It's
Yeah, it's not one-to-one also because of another reason. So to make it more one-to-one than it is.
Because generators.
Yes, exactly. So this will be always also finitely generated as differential algebra. and just I go from equations to algebra. What is solution in terms of algebra? So any solution, I will say solution of A, where A is a differential algebra, is a differential homomorphism from A to power series. Because generators of this algebra are actually images of my variables, and their images under this homomorphism are solutions. Okay, so and then the theorem, this one can be restated that if A is the domain, and its transcendence degree over C is 1, then all solutions are convergent.
What's the actually other counterexamples for non-domains? What's wrong with them?
You cannot talk about transcendence degree
Why
that
not?
easily.
Like if you say something about supreme components, you
Yeah, so if it will just make things more technical. But
Okay.
yes, you can say that. So if every prime component is transcendent degree 1, then this will also work. Because whatever solution you take, it is a solution of sum of prime components. So yes, that's actually a good
Right.
point. So this will work in non-domain case, but just things will look much more technical.
Okay, but so it could be that this first bullet might look scary to people who don't want to talk about differential algebra, and this result might look more.
Yes, that's right. But then you see, this is actually good questions to think how to present it in
Different audiences.
to different audiences. Because like if I omit this, then I will have to write more here.
Not necessarily. You can just say it a little vaguely. And,
Yes. Oh, so but if I want to formulate the result, then I will have to do something.
Because
Or I can say vaguely. Yes,
one
you're
still
right.
talks about dimensions of not irreducible varieties. It's still allowed. And,
Yes, that's right.
So how is this theorem different from this one?
It's a formulation. It's
Oh,
a
just
formulation.
reformulation,
It's
okay.
just a formulation.
Oh, okay, all right.
All solutions are convergent. It's just a formulation for to make the
So,
what follows easier. So and now this theorem is actually constructed from two facts. One fact that we call proposition. Both facts have nothing to do with differential algebra, but they have certain differential algebraic interpretations. So I consider the following system of
so it's not true they don't have anything to do. They have interpretation.
yes, right.
One might think that
They don't look like statements from differential algebra.
correct. So let's go.
So consider the following system of ODs. Where 1.pn are just polynomials. Then,
And n equals n.
pardon?
same n.
Same n, yeah, same n. Then every solution is convergent. So this is a fact purely from differential equations. You can just bound Taylor series coefficients, whatever. But what that means for us is that if our differential algebra A is finitely generated as just commutative algebra over C, then I'll search second version. Because in differential algebraic terms, existence of such system of equations actually says that it's finitely generated. So you can find finitely many generators so that every derivative is expressed in them polynomially. So this looks simple, but this is more or less the main tool for today. So convergence is implied by finitely many generators as algebra. Okay, this was the first ingredient. And then the second.
And it doesn't use the transcendence degree requirement.
No, yes, that's completely general. Yes, so, and actually this can be thought as another criterion. And now, something with transcendence degree, it again will first look like something not from differential algebra. This is second ingredient, and this is a following proposition. So assume that R is a domain over C. It's not differential algebra, just usual commutative algebra, and transcendence degree over C, R is 1. Then the following happens. So if I have two more domains,
could you clarify how this corollary, not good, but how would something like this fail in that example? So what was wrong with that example?
That's a good question. Unfortunately, I have raised the example. So in that example,
You can't.
I can maybe just
X, y dot.
Okay,
It's a polynomial.
yeah. So what you had in that example, right here for a moment, you had x squared times y dot is equal to something. So in order to write y dot in terms of the rest, you have to divide by x squared. So, and this doesn't mean that this algebra is not finitely generated, but this means that it's not straightforwardly finitely generated. And then one can check it's actually infinitely generated because of this division. Although it's not a proof that it's not finitely generated. It's true here.
But you can prove that by...
Yeah, I can prove that because the corollary fails. Yeah, sure. So, yeah, that's correct. That's correct. So, now if I have such...
There's proven theorems in algebra by using differential
By using analysis.
That's amazing.
That would be cool. That would be cool, actually. Yes. So, yeah, so now if we consider this chain of domains, so this is a field of fraction of A, then if T is finitely generated, then S is finitely generated.
What's A?
Oh, sorry, R. So somehow in transcendence degree 1, the property of being finitely generated obeys, somehow if you bound from above and from below by finitely generated algebra, the middle will be also finitely generated.
In this case.
In the sense degree 1 case.
But if not, then.
If not, then it's not true.
Not necessarily true.
Not necessarily true. So for the sense degree 2, there is counterexample. And actually, it can be also derived from the counterexample for differential equations.
Uh-huh.
So again, this is purely a commutative algebra statement. There are no differential derivatives there, but it has the following corollary.
Could you put quantifiers there? If
So R is the main. Then for every
so for every R.
yeah for every
S and
okay
T.
so every R
Oh,
every R domain, and then every S and T.
Uh-huh.
T is finely generated implies S finely generated. Okay, that's fine. So and then corollary. So if A is differential algebra, so A is a domain and percentage degree is equal to 1, then A is finely generated as just algebra.
A and R are the same thing now again?
No? What?
You mean
Okay,
this
no,
is
it's okay.
a differential domain?
Yeah, differential domain. So A is this A. I fix this A
Okay.
more or less forever. So then A is finally generated as commutative algebra. So the implication from this proposition to corollary is not that straightforward, but roughly speaking, so you have A, and you can find, so A will be like S in this situation. You can find something which gives you transcendental degree 1. You can take any transcendental element inside. And then the question is how to bound from above by something finely iterated. And this can be done, roughly speaking, if you just invert all separants. If you invert all separants, then you will get something finely generated and larger, and then you will get finite generation for the algebra itself. And now the theorem is actually modulo these two propositions. Theorem is proved because we know that the sentence degree implies finite generation, and finite generation implies convergence.
So if the transcendence degree is greater than 1,
Then you don't have such statement, at least straightforwardly such statement.
in that generality.
Yeah.
But can you use that kind of argument in certain cases?
I mean, you definitely can use this corollary. This corollary is not dependent on the sentence degree.
Yeah, but this is sort of like a orthonormalization in some vague sense. I mean, that's what it goes back to what you did several years ago.
Yeah, I actually will mention this result a little bit later, but not here. So, no, I think, like even in commutative algebra, having finitely many generators is quite the subtle thing. So it's hard to tell. And there are a lot of infinite generated subalgebras, even in polynomials into variables.
Could you give an example for those who have never seen that?
Okay, sure. So, an example why this fails for two variables is the following. So, you can assume that I live in algebra over C into variables, x and y. So, this will be my larger algebra. Then, smaller algebra will be, let's just write it some different. Sorry. C of x, xy, this is something finely generated. Then it can be considered as subalgebra of C, x, xy, xy squared, xy cubed, ... And this is subalgebra of CXY. And one can show that you cannot generate this by finitely many elements. Although these two algebras are finitely generated. That's how it fails in to some degree too. And actually, I don't know any easy way to fix that. So this is
Fix minimum.
you mean impose some additional restriction here to make it working for to some degree too. Okay, any questions so far?
And can you still encode something like this by those kind of equations?
By these kind of equations?
Yeah.
No, because this kind of equations is exactly the kind of equations which leads to finite generation.
Yeah, but so that's exact. So I mean, this is not exactly, but
It leads.
It leads. Yeah.
Yes, yes.
So this.
Although, if I allow them to be rational functions, then
Yes.
things will change.
So
Such appear a lot. So this is.
Yes, yes, sure.
how does this example contradict the proposition?
This proposition,
Yeah.
because if you replace this 1 by 2,
Yeah.
then this will be r,
Yeah.
this will be what, t, and this will be s,
Oh, that's T. I see.
and r and t are finitely generated, and s is not.
Okay. Sorry. Okay.
Okay, so yeah, I'm going a little bit over time, I think. So how many time do I have?
Thank you.
I'm not going.
over time. No.
Oh, it's until 11:30. Sorry. I just computed wrong in my head. So yeah, so
Don't raise it. What do?
oh, just
That's fine.
That's
really.
okay. So this is all this theorem. Okay, this is nice, and at least for me, it's actually striking that such an algebraic property forces something like analytical like conversions. However, to some degree, one is okay. It's somewhat restrictive, so you cannot apply this theorem to really large systems.
All right,
Because the sense degree, roughly speaking, is number of unknown constants like in solutions, and this is like one unknown constant. So
this is basically an order one.
Basically,
Differential equation.
it's basically order one nonlinear differential equation. So that's actually it often happens. However, we would like to go a little bit further. So, and for going a little bit further, let me introduce a notion of rank. So, yeah, notion of rank is
A. A is what?
A is still differential algebra. A is differential algebra for the rest of today's talk.
Over C.
Over C. So, and this is supremum of transcendence degree of E of A over C, where phi is actually a homomorphism from C to C of T. So I consider all solutions, and I consider transcendence degree of the image. So, and then it's not big deal, but you can just from this theorem you can deduce the following theorem, that if rank A is equal to 1, then all solutions are convergent. So the reason why this statement follows from this one is that now I can, if I consider any solution, I can now consider this image and apply the theorem to the image. So it's not a big new achievement. It's somewhat restates the theorem.
It's a corollary.
It's a corollary. Yes, I call it theorem because it's just a theorem from another paper. I talk today about two different papers. So, and so the first natural question is whether this theorem is any better than this one. So, does there exist algebras which are rank 1 but not in degree 1?
So in your theorem, does it have to be a domain here?
Not really, because its image is domain. Its image is always domain because it is in a domain. So it's yeah, I don't need it. So what to erase? Let me maybe erase that. So first I'm going to explain why this theorem is something more than this one. So to show the example which satisfies requirements of this theorem, but doesn't satisfy requirements of this theorem. And then I will explain actually why this theorem is from my point of view has big explanatory power.
It's what?
Explanatory power.
Could you rephrase this? I don't get it.
Okay, then I will explain why I like this theorem.
Okay.
So first, the example why these theorems are different. So we can consider example. We can consider algebra with a lot of new constants. So you can consider algebra with generators, let's say x, y, and c1 dot cn maybe. Yeah, okay, let's make it extremely simple. So these are generators. And I also have equations that the derivatives are all zeros. Okay, then my A will be isomorphic to just polynomial ring, so it will have transcendence degree n, but every homomorphism will actually have transcendence degree or even 0. So because this constant have to go to some constant in C. So then for every from differential homomorphism C, transcendence degree of A is actually 0. And this example, it's somehow, okay, it's artificial, but it says a lot in the sense that it says that this rank will be different from transcendence degree when you have conserved quantities, when you have new constants. And this is what you have a lot in physical systems, and in some sense, in physical systems, you often have number of conserved quantities equal to dimension of the system. So you have really many of them usually. So this example shows that this theorem is more than this one, and moreover, what does this rank A means? So when you have an image of A, this means that you just have power series which are a solution of system of equations, and this power series they generate something of transcendence degree 1. This means that in phase space, you have a curve. And this is what usually happens with physical systems, because physical systems are usually nicely parameterized by time. So for each time moment, you have, this is very natural assumption for physical systems in this sense. That's why I like this theorem, because it's kind of general. However, there are two questions which are arise. One is a question of effectivity, because, okay, I can check whether transcendence degree 1 using some computer algebra, but whether I can check this condition is not that clear. And I will talk about it in a moment, but before, I have a question maybe to Ronnie, because when I see rank in a context of differential algebra, I immediately try to find my Occam's razor. Occam's razor. Anyway, I'm just surprised at this new notion. That doesn't coincide with anything we already have. I looked through definitions of Morley rank, of U rank, and it didn't look immediate for me. Is it something?
Does not look immediate for me too.
Because this notion of rank is very geometric. It's like the dimension of your curve in phase space. And if it will coincide with something known, that would be actually good.
Excuse me, your phi is over C, is that right? They are homomorphic over C. They leave constant fixed.
Yes, it's over C. It's differential homomorphism over C.
Yeah.
So
the algebra A over there would just
yeah. So for every homomorphism in the example, you have to map C1
Back to-
and
back to
Cn
C.
to some constants.
when you say constants, it could be transcendental constants
Yes.
over C.
Yes, because this is what you usually have, these integrals of motion. Energy, momentum, all they are constants, transcendental constants over C. So this is a prototypical example.
So
in
in
sense.
other words, even though A has a
Large
huge transcendent degree,
Yes, and this is what usually happens because in mechanics they have this Noether theorem that you have usually you have many integrals of motion.
right?
And every integral of motion, it drops to some degree by 1,
Yeah.
roughly speaking. So, and this rank 1 is what you will get for reasonable mechanical system or reasonable physical system, unless something blows up.
Let's not call other systems unreasonable by this, but
Yeah, okay.
there is a good supply.
There is a good supply of systems that when this is true.
Like when,
Okay.
like when a particle is traversing a path.
Yes. So there are many interesting physical phenomena. Then this is not true, and that's why they're interesting. So, however, okay.
One of the reasons that.
Yes. Yeah, and now I would like to talk a little bit about effectivity of that, because it's unclear how to check that algorithmically, verify this condition. So, and it turns out, and this is a more serious theorem than this one, so that I can erase this. You can get at least partial answer algorithmically. So what you can,
Your result, right?
no. So it will be, what I will say will consist of two parts. One is result of Gauss-Mundus-Muslim, and another is a result of myself, you, and Tjör. Okay, so yeah, so let's introduce a polynomial. It's a differential polynomial. There Hm is the Wronskian of all monomials in X and Y of degree at most M.
So
Yeah.
sorry to interrupt. Just to go back to what you were asking. So you interpret phi as a solution,
Yes.
and so supermember phi A. So how do you interpret such a phi that makes it happen? As a generic solution, maybe, or something like that?
No, it's just supremum. I have a lot of solutions. I have a lot of numbers, and they take a
I
supremum.
think he's asking if there are the ones that hit.
Yeah, the one that.
Do they have some
Yes.
special meaning, or do you have to give a name to it?
I'm afraid this then it hits supremum, and if supremum okay, in the example I had of divergent series, it is usually 1, but then when series is divergent, then it's 2. Okay, so when it hits supremum, it's actually not a generic, but it's often contrary.
Okay, so you might give a definition of singular by saying that it's
By this, okay, yeah. So then we might not have. I'll have to verify it in more.
Yeah, okay, then it will be interesting to discuss.
Yeah.
Might have or might not?
Might not.
Might not.
Yes.
Okay, that's interesting. It might not have.
Okay, so you can write this Wronskian, this is like a huge matrix of all monomials in x and y. And vanishing of this Wronskian will just say that monomials in x and y of degree at most m are linearly dependent over constants. That would mean that x and y are algebraically dependent and algebraic relation within them has degree at most m. So, and then we can use that for make an effective version of the semi-effective version of the statement. So let's call it also theorem. So rank A is equal to 1 if let's first name generators of A. So let generators of A be 1xn, then rank A is less than or equal to 1 if first, if there exists M such that you have this Wronskian is nilpotent and also this Wronskian.
Is this for all ij?
Yes, this is for all ij and this is for all I. So this, like, what this theorem says, it's pretty reasonable. So it says that if there is some degree, so that all generators are algebraically dependent over constants of this degree, and generators and their derivatives. So if you are given M, some certain M, then you can verify these two statements either using the Fed-Grobner algorithm or using an explicit bound for effective differential Nullstellensatz, which is a result of myself, Alexei, and Theo. So, however, so you can, with this algorithm in hand, you can verify that certain M works. But of course, you cannot look at all infinitely many M's. So this theorem doesn't give an algorithm to check this criterion, this statement, but it gives a method to show that this is true. So it's algorithm only in one direction. Yeah, good question.
And there is no upper bound?
No upper bound. No upper bound. So I wouldn't be surprised if one exists, but not now.
And have you some bunch of examples showing how big M could be?
Yeah. So one famous example is first Kepler's law. So so let me just example. Oops. Example. This is the first Kepler's law because what Kepler's law says that if you have.
Could you write down the name?
Yeah. Okay. So example will be first Kepler's law, which says that all planets move quadratic curves. So, and you can deduce Kepler's law from Newton's law of gravity. So moreover, Newton's law of gravity gives you a differential equation, because it says the force is equal to something. And then with these differential equations, you can check that for m is equal to 2, you have that h2 of x and y, of two coordinates, is nilpotent. That would mean that planets indeed, planetary motion is indeed by curves of degree 2. So, again, there is a bunch of supply of physical systems that the motion is along the curves of not high degree, 2, 3.
So is this m, you think, equal to the order of the equation, or is because of the degree of the curve?
Because of the degree of the curve.
Yeah.
So m is the degree of the curve.
M is the degree of the
M is the degree of the curve, and okay, usually you don't see curves of degree 100 in moderate motion. Of course, you can find examples in this. So again, there is a big supply of examples where this m is relatively small. Although I don't have any a priori bound based on equations.
Excuse me. When you write down up there x sub mxy equal to the differential polynomial ring over xy?
Oh,
Belong.
thank you.
Okay, all right.
Thank you. Okay, so and just as I promised to mention, another normalization is that, so this notion of rank, it's meaningful as long as your algebra is of finite sense degree. Because what one can show that if, let me write it somewhere. Let's say statement. That if A has a non-zero differential to standard degree, then
So it's also over complex?
also over complex, but differential to standard degree. Then rank A will be always infinity. And this actually follows from the differential Noether normalization.
From your theorem.
From my theorem.
Well, but in any case, yeah, okay. But there are many
So
examples when.
yeah, so this statement somehow shows like an upper bound from where it doesn't make much sense to go. But I think many examples arising in sciences, they actually have finite sense degree. Usual, so 0 to sense degree differential. So you have non-zero differential sense degree. Usually, if you have like control parameters, so you have the control function. But that's a separate story. So and
That's it?
yes, that's it.
Thank you. More questions?
After this is turned off?